Hello everybody, welcome to AS Engineering Academy and AS online platform. So here we are to discuss about the important topics and the preparation strategy about the power systems. Right? And myself Prasad Meghavarna and I'm doing my PhD in SV University, Tirupati. So actually I'm having 12 years of teaching experience in only power systems. Now coming to the syllabus of power system. So this is the syllabus of power system. It consisting of generation of electrical energy, transmission and distribution of electrical energy, and power system analysis and the switchgear and the protection. So see here students, so we know, so already we have discussed the power system itself is consisting of approximately 13 to 16 marks of overall weightage. So we can say the total weightage of the power system is consisting of 13 marks to 16 marks. 13 marks to 16 marks. In that particularly, if you go for generation of electrical energy, the generation of electrical energy is having very less weightage in gate, right? And coming to transmission and distribution, it is having somewhat more weightage, and power system analysis, we can say faults and stability and the load flow analysis, it is having more weightage. And switchgear and protection is also, it is having a somewhat less amount of weightage. Coming to total 13 to 16 marks, we can say, or we can expect approximately, so 5 to 6 marks in only transmission and distribution, and 7 to 8 marks in the faults and stability or power system analysis. The power system analysis is consisting of various parts like the fault analysis, stability analysis and the load flow analysis. So the power system analysis, the major core of the entire power system, right? So it consisting of load flow analysis, and it consisting of the stability analysis, and it consisting of the fault analysis. So to understand the load flow analysis, we have to study about the various parts like the bus admittance matrix and bus impedance matrix. And to understand the fault analysis, we have to study about the unbalanced power system analysis, like the symmetrical component theory analysis and as well as symmetrical network construction, right? And coming to stability analysis, to understand stability analysis, so we need to understand the basics of power system, basics of balanced power system, and we need to understand how to stabilize the system, right? So if you see, so already we have discussed this is the weightage of entire power system analysis, right? It consisting of approximately 7 to 8 marks of weightage in case of gate, and 4 to 5 marks in case of engineering services, objective, prelims, and 50 to 60 marks in case of the conventional. Now coming to weightage in case of gate, that means number of questions we got in gate in 2018, 2019, 20 and 21, 22. So we are getting approximately minimum of 2 questions and a maximum of 3 questions in 1 mark, and minimum of 2 questions we are getting in 2 marks. So that 4 marks and 2 marks, that means minimum of 6 marks we are getting every year, right? Sometimes it may be 7 marks, or sometimes it may be 8 marks, or sometimes it may be 10 marks also we are getting only in the fault and stability analysis part. And these are the number of questions we are getting in case of engineering services prelims and the mains, so objective and conventional examination. So we are getting 6 marks, 4 marks, 3 marks and 4 marks and 3 marks. So that at least we are getting 3 to 4 marks we are in power system stability, power system analysis, and minimum of 40 marks in the engineering services mains, right? So coming to the syllabus of power system analysis, students, here it consisting of several topics or several chapters like basics of balanced power system, and representation of power system network in per unit form, and matrix representation of power system, and load flow analysis, and basics of unbalanced power system, right, where we are going to discuss about symmetrical component theory, and construction of symmetrical networks, fault analysis and the stability analysis. Please check here. In the last class, so we have discussed about the preparation strategy of power system analysis, in which We have discussed in case of basics of balanced power system, we have to discuss about the basics of single phase power transmission as well as basics of three phase power transmission. In case of basics of single phase power transmission, we have to see how to calculate the active power and reactive power at a load. Active power and reactive power at a load in a single phase system. So as a form of complex power. Similarly, in case of three phase system also we have to calculate how to calculate the active power and reactive power in case of a three phase load. So in terms of complex power, right? So whenever you are calculating the complex power, so we can get so the active power and reactive power as well as the magnitude of the apparent power and the power factor angle, and from that one we can calculate the power factor of the system. Please see here students, the first chapter is common for entire part. So not only for this part, the first part is common for entire power system, right? It may be protection or it may be generation or it may be transmission and distribution or it may be power system analysis. Whenever you are learning the basics of three phase and single phase power transmission, so where we are calculating the complex power and where we are calculating the instantaneous powers and instantaneous voltages and instantaneous currents as well as the power transfer equation, that will be common for entire power system, not only for power system analysis. And coming to the second chapter, representation of power system in the per unit form. So whenever you are representing the power system in per unit form, actually we are facing some problems in the absolute form of representation. So to avoid that difficulty, we are going for the per unit system representation of the power system. So whenever you are representing voltage in terms of volts, current in terms of amperes, power in terms of different powers you are having, right? Active power, reactive power and the apparent power. So whenever you are having different terms of power, we are having different units. So to avoid the difficulty in the calculations because of this, right? That means we are having several units, several terms, as well as we are having one transformer also. So to avoid that difficulty, we are going for the per unit system representation. Actually, the transformer which is present in the single line diagram or in the power system, it is going to give more complexity. Why? Because of the transformer is a mutually coupled circuit. It is not electrically coupled, but it is magnetically coupled. So because it is providing some discontinuity path in the entire power system network. So how many transformers are there, that many discontinuity path we are having. So that to avoid that difficulty, we are going for representation of power system in the per unit form, right? And later on we are seeing the matrix representation. So we are calculating the bus admittance matrix as well as the bus impedance matrix. So Y bus formation and Z bus formation we are saying, and the properties of Y bus, the properties of Z bus, right? The definitions of Y bus elements and the definitions of Z bus elements also we are seeing. And later on, the bread and butter of power system, we are going for the load flow analysis. Students, the load flow analysis, without performing load flow analysis, we are unable to perform the power fault analysis and the power system stability analysis. So if you see clearly, I have given load flow analysis and fault analysis and the power system stability analysis in green color. Why? Because they are the major portions. They are the major portions of entire power system analysis. If you want to understand these three, you have to study remaining parts, right? So basics, per unit form and Y bus and Z bus. So we are studying to understand load flow analysis, and we are studying the basics of unbalanced power system and symmetrical network of power system. We are studying to understand fault analysis. And power system stability analysis, we need the per unit system analysis as well as the basics of the power system, balanced power system we can say. So without studying all these three, we are unable to analyze these power system networks. Please listen carefully. So if you want to analyze the power system components, right, that means load flow analysis or the fault analysis or the stability analysis, we need these basics parts very clear. Basics of balanced power system, per unit system representation and Z bus and Y bus formation, Y bus and Z bus formation, bus admittance matrix and bus impedance matrix formation, and basics of unbalanced power system, where we are studying the symmetrical component theory, symmetrical component theory, components we can say, symmetrical components and the symmetrical network representation of the entire power system. So we are having different power system elements like a generator, transformer and the transmission line, and we have to study the symmetrical networks of several elements. And whenever we are going for that one, and we are going to get the fault analysis. So in fault analysis we are going to study about various types of faults like open circuit faults and the short circuit faults, and in various types of open circuit faults and various types of short circuit faults we are having, and finally power system stability analysis. So these are the textbooks we can prefer, students. We can go for the power system analysis by Stevenson and Greger, one of the best textbook of entire power system. Power system analysis by Stevenson and Greger. See here, students, this is the one of the best textbook. And we can go for power system analysis and design by Duncan Glover. So this textbook, this particular textbook is consisting of case studies. So how they are going to ready, how we are going to write each and every chapter. So to write each and every chapter, so they are giving case studies for each and every chapter. Clear? So one of the best textbook we can say, the power system analysis and design by Duncan Glover. The examples are very super in that power system analysis and design. And in power system analysis by Stevenson and Greger, the examples are very good. Actually, as well as we can go for practice problems also. So we are having very good practice problems in these two textbooks, right? Not only on those two, remaining two also we are having very good examples as well as the practice questions. Coming to electric power systems by John Wheely publications. So whenever John Wheely publications are publishing a textbook, so we can definitely trust that textbook as one of the best textbook of our system. See here, so this textbook is also providing having various good examples and very good theory content and practice problems. And the great professors of India, so they have given D.P. Kothari and I.J. Nagarath. So they have given modern power system analysis, a very good textbook of power system, right? So we can say all these four textbooks are equally important, right? You can pick up any one textbook, no need to take all the four, right? Pick up any one textbook and try to prepare. Clear, students? Actually, whenever you are attending the classes in ACE Engineering Academy, no need to take these textbooks. So we are giving everything. We are covering the content of all the four textbooks, not only four. So along with this, we are having several textbooks like the Havari, right, and Hadi Sadat and Devi Priya Das. We are having several textbook content, J.B. Gupta, C.L. Wadhwa, right. So those textbook content we are covering, and almost that means you are able to give the solution for almost all 99.99%, right? We can say 100% also of engineering services examination questions and as well as the gate questions also. Clear, students? So whenever you are solving by reading our notes, right? So we can give a guarantee that you are able to solve almost all the solutions of the previous gate as well as the engineering services questions. Now, so this is the thing what you have to practice. You have to practice the previous engineering services questions as well as the Indian administrative services questions, right? So previous UPSC questions we have to practice, and previous PSU questions we have to practice, and previous gate questions we have to practice, and previous electricity board of different states like Transco, Genco and Discoms we can practice. And we are going to discuss almost all these type of questions, several varieties of questions in the classroom itself, and we are providing the best notebook, all right, the best content for you. Clear, students? Now, so in the last class we have seen the important topics of each and every chapter. So these are the important topics of the basics of balanced power system, So we are studying about operator J and power transfer equations and basics of balanced star connection and delta connected system and complex power calculations, right, in terms of the three-phase system. And this is the per unit system representation, and these are the contents we are studying. Electrical equivalent networks of the power system elements we are studying, and later on per unit system representation. So we are giving the definition of per unit system in that, and later on we are going for per unit system calculations or representation of power system in per unit in terms of single phase system as well as in the three phase system, and advantage of the three phase system and construction of the per unit impedance diagram. So we have discussed already the most important topic in this one is the per unit impedance diagram. Per unit impedance diagram. But whereas in chapter 1 almost all the topics are very, very important. So you should have that means we need a very clear cut idea about the basics of the single phase as well as three phase balanced power system analysis. So whenever we are understanding that balanced power system analysis, then only it will become very easy to analyze the unbalanced power system analysis, so that we can go for the fault analysis and the stability analysis. And we need basics of balanced power system and per unit system analysis as well as matrix representation to analyze the load flow analysis. So the matrix representation, we need the bus admittance matrix and the bus impedance matrix, Y bus and Z bus, we need to calculate or to know the load flow analysis. In case of load flow analysis, students, so the great professor of India, so D.P. Kothari is saying that it is the bread and butter of entire power system. See here, so whenever we are going for load flow analysis, we need the admittance quantities or the impedance quantities. Most probably we can go for the admittance quantities. Why? Because the calculation of admittances are very simple compared to that of the impedances. When you go for actual calculations, we can get those advantages. And the definitions of Y bus elements, and along with that we can go for the properties. The properties of Y bus. So we have to study, right? So in that properties of Y bus, we are going to get, so it is a square matrix, it is a symmetric matrix, and it is a sparse matrix, right? And what the diagonal elements represents, what the off diagonal elements represents, all those things we are going to see in the properties of the Y bus. And the problems of on the Y bus, definitely they are very, very important. So whenever a network is given, constructing Y bus, whenever Y bus is given, constructing a network, and so analyzing the individual elements of Y bus by knowing the definitions of Y bus elements, that is very, very important. And coming to the bus impedance matrix, so in the recent years, in the past 10 years, we are not having any question in the bus impedance matrix in gate. I am saying only in gate. But in the remaining exams, they are asking the questions in the bus impedance matrix. It may be engineering services, or it may be any local state government exam. So, or it may be SSC JE, or it may be RRB JE. So they are asking the questions in the bus impedance matrix, students. And the definitions of Z bus elements and along with the problems on Z bus, we have to prepare definitely. Clear? Right, and coming to the next chapter, so the bread and butter of entire power system, we can say the load flow analysis, the very most important chapter. Very most important chapter. So where we are studying the iterative methods like Gauss method, Gauss-Seidel method, Newton-Raphson method, and decoupled method, and the fast decoupled load flow method, and the comparison between the load flow methods. So these are the most important concepts that you have to concentrate in the load flow analysis, students. Clear? In case of static load flow equations, so we will get the active power and the reactive power equation at any particular bus I, right? So we are going to calculate the active power at any bus I and the reactive power at any bus I, and we can analyze the terms of active power and the reactive power, and based on that one, these active power and reactive power, are consisting of two particular variables. They are delta at ith bus and magnitude of voltage at the ith bus. So we are having delta and magnitude of voltage as the variables at every bus, and P and Q are the functions of delta and voltage. So if you see, finally we are having P, Q, delta and mod V as four variables. So P, Q, mod, delta and mod V, we are having four variables. So to analyze the load flow analysis in these four variables, we are taking that 2 as known and 2 as unknown. So 2 variables as known parameters and 2 variables as unknown parameters, we are going for the load flow analysis. So that we are going for classification of buses based on that static load flow equations. So we may be having P and Q are known, so that it will be PQ bus, and P and V are known, that will be PV bus, and delta and V are known, that will be a slack bus. So we are having PQ bus, we are having PV bus, and we are having a slack bus. So based on the static load flow equations, we are classifying the buses in the entire power system network. And based on bus classification, and we are going for the iterative techniques, Gauss method and Gauss-Seidel method, Newton-Raphson method, and decoupled and the fast decoupled load flow methods. So in this, Newton-Raphson method is the most important method, so we have to study. So in this, the finding the size of Jacobian is the most important concept in the Newton-Raphson load flow method. And sometimes they are asking the questions in the Gauss-Seidel load flow method is also they are asking. And particularly coming to the gate, they are not asking the questions in the decoupled method as well as the fast decoupled method. They are not asking the questions. But engineering services, they are asking the questions. So in the decoupled and the fast decoupled methods as well as in the comparison portion also, right? And the Gauss-Seidel method is the just an advancement of Gauss method. So in case of Gauss method, we are calculating the voltage and delta at any particular bus I. Just an advancement of Gauss method in Gauss-Seidel method, we are updating the quantities. Just by updating the quantities, we are studying the Gauss-Seidel load flow method. Clear, students? And try to understand these concepts very clearly, and in particularly Gauss method. That means if you want to understand Gauss method, we need the Gauss-Seidel method. If you want to understand the Gauss-Seidel method, you need the concept of Gauss method very clearly, and the Newton-Raphson load flow method also, right? And coming to the basics of unbalanced power system. So here they are asking the questions in the symmetrical component theory, so which is given by CL40Q. CL40Q. The symmetrical component theory is given by CL40Q. According to CL40Q, any unbalanced system can be resolved into set of several balanced systems like a positive sequence system or negative sequence system and the zero sequence system. Clear? And representation of entire power system in the symmetrical component form, and steps to analyze the unbalanced system, right? So we need this chapter, particular chapter, to go for fault analysis only. So there are no direct questions exactly. If you are expecting any question, particularly from chapter 5, we cannot expect. Why? Because so we are studying and we are understanding this chapter only to analyze the fault analysis of the system, right? And coming to the next chapter, the symmetrical network representation of entire power system. In this, we are studying the symmetrical network representation of several elements like star connected networks, delta connected networks, star connected generator, delta connected generator, and the transformers, transmission lines, synchronous machine and the induction machines, which means synchronous motor and the induction motors, and the problems, right? So it is one of the most important chapter, but still we are studying this chapter to go for the fault analysis only. So whenever if you want to solve any problem by using in the fault analysis. It may be any fault. So single line to ground fault or double line to ground fault or double line fault or symmetrical fault. So we need the symmetrical network representation of the individual power system networks. Clear? And coming to the most important chapter, so without expecting a question in this one, right, we cannot expect a question paper, right? It may be GATE or it may be engineering services or whatever it may be. So without a question in this one, so we cannot expect a question paper. So here we are studying the types of faults and the consequences of the open circuit faults as well as the short circuit faults. See here students, in case of this one, whenever we are going for the types of faults, what are the types of faults we can expect? The types of faults are two only. One may be a series fault, one may be a shunt fault, right? So we are having two types of faults. One is the series faults. The series faults are also called as the open circuit faults. Open circuit faults. And the second one is the shunt faults. The shunt faults are also called as the short circuit faults. The series faults are the shunt faults. Simply we can call them as the open circuit faults or the short circuit faults. Clear? These are the two types of faults we are having. And coming to the consequences and the causes of these faults, see here students. So whenever you are going for open circuit faults, in case of open circuit fault students, suppose we are having a three-phase generator. This three-phase generator is consisting of three transmission lines, phase A, phase B and phase C. Right? Whenever only one conductor is opened and remaining two transmission lines are safe. And this fault we can call it as one conductor open fault. Suppose if it is phase A and if it is phase B and if it is phase C, in this case the phase A current is 0 and phase B current is not 0 and phase C current is also not equivalent to 0. So only one conductor current is 0. So that we can say it is one conductor open fault. Right? And before this, in chapter 1 we have studied about the basics of balanced power system. In case of balanced power system, so we have studied the conditions for a balanced system. What are the conditions to be satisfied for a balanced source as well as a balanced load. So based on that one, we can say that one of the consequence of this open circuit fault is nothing but the system will become unbalanced. So because of this one, the system will be unbalanced. The system will be unbalanced. Right. And suppose whenever you are having two conductors open, suppose if it is the generator and if it is one conductor where IA is equivalent to 0 and one more conductor is also open where IB is equivalent to 0 and one more conductor is safe, right? So here IC is not equivalent to 0. So in this case, this type of fault we can call it as two conductor open fault. Two conductor open fault. So it is a two conductor open fault. So these are the two types of faults we are having, one conductor open fault and the two conductor open fault. And coming to the students, suppose if all the three conductors are open, suppose if you are having a generator, if all the three conductors are open, one conductor is open, one conductor is open, and one more conductor is also open, and one more conductor is also open. If all the three conductors are open, so here we can say IA is equal to 0 and IB is equal to 0 and IC is equivalent to 0. So IA is equivalent to 0, IB is equivalent to 0, as well as IC is also equivalent to 0. When all the three currents are equivalent to 0, we cannot say it is a fault. It is, we can say the generator is operating under no load condition, right? So we cannot say it is a fault. It is not a fault. It is not a fault. We can say the generator is operating under no load condition, right? So it is the no load operation of the generator. No load operation of generator, right? So that we are having only two types of open circuit faults. One is one conductor open circuit fault and the other one is two conductor open circuit fault. Clear? And the consequences of these open circuit faults, when our conductor is open, current will become 0, so voltage will become increases. So that the consequences of these open circuit faults, the consequences, whenever open circuit faults are occurring, we can say the current in the system will be reducing, and because of that one, voltage will be increasing. So whenever voltage is increasing, we can say the insulation of the loads which are connected to that one will be damaged. So insulation fails. Insulation fails. Whenever the insulation is failed, then we can say the short circuits will occur. So because of open circuits, we are having short circuits. Short circuits will occur between the conductors, and because of that one, more heat will be produced. So more heat will be produced, so that the equipment will be damaged. So equipment will be damaged. Equipment will be damaged. Right, students? So these are the consequences. And as huge load is disconnected from the generator, the generator is free to rotate. As the generator is free to rotate, so we can say the speed of the generator will be increased. Whenever the speed of the generator increased, the frequency of the generator will be increased, right? So we can say as huge load is disconnected, huge load is disconnected, so that the generator is free to rotate. Generator is free to rotate, so that the synchronous speed or the rotor speed will be increasing, and that rotor speed is more than that of the synchronous speed, so that the generator is coming out of the synchronism. Therefore, the synchronous generator will become unsynchronous, or so asynchronous generator. and because of that one, the stability of the system will be reduced. Stability will be reduced. As whenever the speed is increasing, the speed formula is equivalent to 120 f by p. So the number of poles are always constant whenever speed is increasing. As a result of this one, the frequency will be increasing. The frequency will be increasing. So that these are the consequences of the open circuit faults. So whenever you are having a open circuit fault, so these are the consequences we can expect from that one, right? What are that? So the current, right, will be decreasing, voltage will be increasing, insulation will be failed. Whenever insulation is failed, so because of that insulation failure, we are getting short circuit between the conductors, and because of that one, more heat will be produced, and because of that one, equipment will be damaged, and as huge load is disconnected, the stability of the system will be reduced and frequency of the system will be increased, right? And coming to the next one, the consequences of the short circuit faults. So before going for consequences, what are the types of short circuit faults? What are the types of short circuit faults? Types of short circuit faults. Types of short circuit faults. If you see clearly, the types of short circuit faults, so whenever you are having a synchronous generator, so this is phase A, phase B and phase C. So A phase, B phase, C phase. Initially, for example students, if this generator is operating under no load condition, suppose operating under no load condition. For example, whenever it is operating under no load condition, what is the current flowing in IA? It should be IA equal to 0, and current flowing in IB is also equivalent to 0, and current flowing in IC is also equivalent to 0. And still we are giving the mechanical input to this one. So we are giving constant mechanical input to this one, PS, and it is not producing any amount of electrical output, right? As it is operating under no load condition. Clear students? Now on this generator, whenever you are getting a fault, suppose if this generator is experiencing a fault, so we will represent that fault with some red color here. Suppose if this is the fault, and even though this generator is operating under no load condition, here actually before the fault condition the current should be 0, but once the fault occurs, this is the fault we are having. So this is the fault we are having. Once the fault occurred, even though this generator is operating under no load condition, the current in phase A is not equivalent to 0, but current in phase B is equivalent to 0, and current in phase C is equivalent to 0. Therefore, one conductor has been grounded. And the fault current in that one, is one phase current. That type of fault we are calling it as the single line to ground fault. Single line to ground fault. Simply you can say LG fault. So even though the generator is operating under no load condition, this type of fault is giving a current in phase A, So that type of fault we are calling it as the single line to ground fault, or line to ground fault, simply LG fault, right? And coming to the next one, the same generator whenever it is operating under no load condition, it is phase A, phase B, phase C, right? And we are having a fault between two lines. So between two lines we are having the fault. So that type of fault we are calling it as the line to line fault. So this is the fault current path. As previously it is operating under no load condition, the current in phase A, phase B and phase C is equivalent to 0. But because of the fault, current in phase B will not equivalent to 0 and current in phase C is also not is equivalent to 0. Please check here students. Before the fault, IA is equivalent to 0, IB is equivalent to 0 and IC is equivalent to 0. The system is operating under which condition? The system is operating under balanced condition. So you can say system is balanced. System is balanced. But whenever you are coming for a single line to ground fault, so without any load in the system, the current is there in fault A, we can say system is unbalanced. System is unbalanced. So we are having only one phase current and we are not having any current in the remaining two phases, students. And coming to this one, here also without any load in the system, we are having a B phase current and C phase current, and this type of fault we are calling it as the double line fault. Double line fault. Double line fault. Or simply we can call it as line to line fault. Line to line fault. Or simply you can call it as LL fault. LL fault. And because of this one also, the system will be unbalanced. System will be unbalanced. Right? And one more fault we can expect on the same power system network. Suppose whenever you are having the generator with constant mechanical input PS, with constant mechanical input PS, and this is phase A, phase B and phase C, right? So before the fault current, before the fault occurring in the system, all the three currents are 0, but whenever the fault is occurred, so these two are grounded, so that the fault current is flowing in this zone. The fault current is flowing in that zone, and we can say the A phase current is 0, but the B phase current is not is equivalent to 0 and the C phase current is also not is equivalent to 0. And in this case the fault current may be the B phase current or the maybe the C phase current, but whereas in this case the fault current is the sum of B phase current and the C phase current. The sum of B phase current and the C phase current, and we can say this type of fault is double line to ground fault. Double line to ground fault. Right? Or we can say LLG fault. LLG fault. Line to ground fault. Line to ground fault. Right? And because of this one is also, the system will be unbalanced. System will be unbalanced. Why? Because only two phases are involved in the fault, and here also only two phases are involved in the fault, and here only one phase is involved in the fault. If any one phase or any two phases are involved in the fault, we can say, so that type of fault as the unbalanced fault or an unsymmetrical fault. And coming to the next fault, so whenever you are having a synchronous generator and we are giving constant mechanical input to this one, and it is operating under no load condition, right? If all the three phases are involved in the fault, right? So here we are having the fault current IF. Here we are having the fault current IF. So that whenever the fault occurring, we can say IA is not is equivalent to 0 and IB is not is equivalent to 0 and IC is not is equivalent to 0. So we are having all the three phases, A phase, B phase and C phase are involved in the fault. So we can say it is a three-phase fault, three-phase fault. So this type of fault we can call it as a three-phase fault, three-phase fault or triple line fault, triple line fault. As the three phases are involved in the fault, we can say the sum of the currents IA plus IB plus IC is equivalent to 0. Always IA plus IB plus IC is equivalent to 0 always. So that this type of fault we can call it as the balanced fault. The system is operating under balanced condition only. Even though there is a fault in the system, so the system is operating under balanced condition. System is still in balanced condition. Balanced condition. So that we can say this type of fault as the balanced fault. So this type of fault as balanced fault or symmetrical fault. Balanced fault or symmetrical fault. And similarly, we are having a fault where we are giving constant mechanical input, A phase, B phase and C phase we are having, and here all the three phases are involved in the fault and they are going to ground, and here it is the fault current IF, right. So here we are having the A phase current IA, the B phase current IB and the C phase current IC, all are not is equivalent to 0. IA is not is equivalent to 0 and IB is not is equivalent to 0 and IC is also not is equivalent to 0. All the three phases are involved in the fault, so that this type of fault we can call it as three-phase to ground fault. Three-phase to ground fault. So this type of fault we can say it as three-phase to ground fault, or we can call it as triple LG fault. Triple LG fault. And here also, as all the three phases are involved in the fault, any fault current will be equally divided into them, so that we can say we are having IA plus IB plus IC is equivalent to 0 as in the condition of the no load system. So in case of the no load system also, we are having IA plus IB plus IC is equivalent to 0. That is why we are calling that system as balanced system. And here in case of LG fault, IA is there and IB and IC is not there. System is unbalanced. And in case of LL fault, we are having B phase and C phase currents only, so that IA plus IB plus IC is not is equivalent to 0. And here in LLG fault is also IA plus IB plus IC is not is equivalent to 0. That is why we are having this fault also. Maybe in case of double line fault, we are going to get IA plus IB plus IC is equivalent to 0. But because of only two currents we are having the system will become unbalanced. So that we can say that type of fault as unbalanced fault, and it is also unbalanced fault, and these two are the balanced faults. So that coming to the classification of the short circuit faults, so we are having first one LG fault, and the second one LL fault, and the third one LLG fault, and the fourth one, sorry, it is LLG only. LLG fault, and it is triple L fault, and the fifth one triple LG fault. Triple LG fault. So these are the classification of faults, types of the short circuit faults we are having. And in this we can say these three are unsymmetrical faults or unbalanced faults. Unsymmetrical faults. Right? Where the system is unbalanced. So in this case, system will be unbalanced. System will be unbalanced. And coming to these two faults, triple L and triple LG faults, they are called as symmetrical faults or balanced faults. Symmetrical faults are the balanced faults, right? So that here the system is still in the balanced condition even after the fault. System is under balanced condition. Balanced condition. See here students, coming to the consequences of short circuit faults, right? So consider a simple power system network. Suppose if you are having a generator and a transmission line and the load. For example, students, the line impedance is Z line and the load impedance is ZL. Clear? And the sending end voltage is Vs and the receiving end voltage is VR in magnitudes. And whenever you are having a short circuit fault, at this location, because of the short circuit fault, the receiving end voltage will become 0. So that because of this one, VR magnitude will become 0. That is the first consequence we can say. Because of the short circuit fault, the voltages will be reduced. So that we are having a low voltage operation in the short circuit fault condition. Right? So that we can say this is the first consequence. Low voltages. Clear? And whenever you are calculating the current before the fault condition, if you calculate the current flowing in the line, that current will be I is equivalent to Vs minus VR divided by Z line. And whenever you are calculating the same fault current after the fault, that fault current IF is equivalent to, as VR is 0, Vs divided by Z line. We can say the difference between sending end voltage and receiving end voltage is very small, right? So that is the voltage drop in the line. And we know that is very, very small. It may be 5% or the 10% of the entire voltage. If it is 220 volts, we can expect a maximum of 5% or 10%, right? So it may be 11 volts or it may be 22 volts nearly, right? So that approximately we are getting 20 volts drop, for example. So that if it is 220, it will be 200. So that we are having very less drop. But whenever, because of the impedance of the system is very small. So as the impedance of the system is very small, right? As impedance is small, only we are having less voltage drop. When impedance is more, drop will be more. Clear? As this is very small, numerator is also very small, the current is also very small. Low only. It is under perfect controlled condition. But whereas coming to the fault current condition, the numerator is 220, right? It is very high. There is no controlling part from the receiving end side, that is 0, and receiving denominator is very small, so that we can say as denominator is very small, it is very low and it is very high. So numerator is very high, denominator is very low, the fault current will be very high. So that we can say the second consequence of the short circuit fault is high currents. High currents. So that we can categorize the short circuit fault as a low voltage and high current. Low voltage and high current. Clear? And also the impedance of the line, if you check here, is approximately inductive in nature. The impedance of line, Z line, is nothing but resistance of the line plus J times of the reactance of the line, and it can be approximated as J times of reactance, where the resistance of the line is very small. And whenever you are calculating the fault current is approximated as the sending end voltage divided by J times of X, and which is nothing but Vs divided by X at an angle of minus 90. Why? Because operator J is 1 at an angle of plus 90 in the denominator, and whenever it is going to the numerator, it will be at an angle of minus 90. And whenever you are checking the fault current is having an angle of minus 90 with respect to the voltage. Therefore, we can say the fault current is lagging the voltage by an angle of 90, right? So that the fault current nature is highly lagging, right? Highly lagging. Whenever you are having highly lagging power factor, so the power factor cos phi, cos of 90 will be 0. So that the power factor is going to 0. Very low power factor operation we are having. So that as a third consequence we can say, we are having low power factor operation. Low power factor operation. And from the power transfer equations, we are having the active power P is proportional to delta, the reactive power Q is proportional del delta, particularly if you want to say, and del mod V. So that the reactive power always proportional to the difference between sending end voltage and the receiving end voltage magnitudes, right, in an inductive circuit. So that here we are having the receiving end voltage is approximately equivalent to 0 because of the short circuit. So there will be high reactive power flow from sending end to the receiving end under no load condition or under faulted condition. So because of this one, we are having high reactive power flow. High reactive power flow from sending end to the receiving end. So under the faulted condition, the power factor will be very low. Because of that one, so we are having high reactive power flow from sending end to the receiving end or fault location. So that this is the fourth consequence of the short circuit fault. So high reactive power flow, so the nature of network will become highly reactive and the power factor will become very low, and voltage in the system are very low and the current in the system are very high, right? And coming to the next consequence, so we are having very high current flow, so that the system will be very overloaded. So the current in the system is very large, so that the loading on the system is very high, so that the system will be overloaded. And because of that one, the frequency of the R, we can say the particularly, first of all we have to speak about the speed. As system is overloaded, the speed of the rotor will be reduced, and that speed of the rotor, NR, is less than that of the synchronous speed. So because of overloading condition, the rotor of the generator will be rotating at low speed condition. so that the rotor speed will be less than that of the synchronous speed. So this speed we are calling it as asynchronous speed, right? Asynchronous speed. And because of this asynchronous speed, the frequency of the system will be reduced. As frequency is reduced, we are having less stability operation, right? So frequency are reduced, we can say, or low frequency operation. Low frequency operation. Low frequency operation. And because of this one, system stability will be reduced. Stability reduces. Stability reduces. So that a short circuit fault we can categorize as, a short circuit fault. The consequence of short circuit faults, we are having low voltage, high current, and low power factor, and high reactive power flow, from source to the load, and we are having low speed operation, low speed because of high current, right? And low frequency operation, and low stability. So these are the consequences of the short circuit faults. Consequences of short circuit faults. Students. So like that, we can categorize or we can analyze the short circuit fault in the system. It may be LG fault, or it may be LL fault, or it may be LLG fault, or it may be balanced fault also. So these are the consequences we are having. Clear? And coming to the equal area criterion, so because of short circuit fault also we are having high frequency operation on the loaded side. So we will analyze that part very clearly and separately, right? But how can you categorize, if somebody asking you a question, how can you categorize or how can you analyze short circuit fault? Means low frequency operation and low speed operation. But in case of equal area criterion, so whenever you are having a fault on the terminals of a parallel circuit transmission line system, or at the midpoint of transmission line system, whenever you are having a short circuit fault, so the frequency of the system of the generator will be increased. We will analyze that one in the equal area criterion separately. But up to now, these points are very, very important, students. Clear? And coming to the types of faults we have studied, LG fault, LL fault, and LLG fault, those are the symmetrical faults. And the unsymmetrical faults are, we are having the triple L fault and triple LG faults. See here, that coming to LG fault, or we can write is LG, we can write as LG. And next one is LL fault, and next one is LLG fault, and next one is symmetrical, triple L or triple LG, any fault we are having. If you see, I will write those some current equations here. So whenever you are calculating the conditions, in case of LG fault, one phase will be grounded. So that in case of this one, so one phase, if VA is equivalent to 0, the remaining phase quantities are safe, right? And coming to the current equations here, in case of current equations, IA1 is equivalent to IA2 is equivalent to IA naught. All are same. All the sequence currents are same in case of LG fault. For LG fault, the sequence currents are exactly equal and sequence voltage sum. What is that? From this one you can say VA naught plus VA1 plus VA2 is equivalent to 0. The sum of the sequence voltage components will become 0, right? And in case of line to line fault, VA1 is exactly equivalent to VA2 and there is no concept of zero sequence component of the current. And coming to the currents, IA1 is equivalent to minus IA2. IA1 is equivalent to minus IA2. And in case of LLG fault, all the sequence voltages are exactly equal. VA1 is equivalent to VA2 is equivalent to VA naught. All are exactly same. Similarly, like LG fault, here currents are equal, their voltages are equal. And in case of LLG fault, one phase component of current will become 0. It may be IA is equivalent to 0, or it may be IB is equivalent to 0, or it may be IC is equivalent to 0. When one current is 0, we can say from this one, IA1 plus IA2 plus IA naught is equivalent to 0. The sum of current components, sequence current components will become 0 in case of LLG fault, and the sum of voltage components will become in case of LG fault. And in case of triple L or triple LG fault, remember the most important condition, all the voltages are equal and 0. VA1 is equivalent to VA2 is equivalent to VA naught is equivalent to 0. All are exactly equivalent to 0. And in case of balanced system, triple L fault or triple LG fault is a balanced fault. So in that case, we don't have negative sequence currents and the zero sequence currents, and we are having only the positive sequence currents, which is IA1. We can say it as the phase A current IA, where IA2 and IA naught are equivalent to 0. And coming to the fault current for LG fault, IF is equivalent to 3 times of EA1 divided by Z1 equivalent plus Z2 equivalent plus Z0 equivalent. Z1 equivalent plus Z2 equivalent plus Z0 equivalent. And coming to line fault, it will be the fault current IF is equivalent to root 3 times of EA1 in magnitude divided by ZA1 or Z1 equivalent plus we can say Z1 equivalent plus Z2 equivalent. Z2 equivalent. And coming to LLG fault, the fault current IF is equivalent to, so EA1 or you can say 3 times of IA naught. Simply you can write it as 3 times of IA naught. Right? And here also it will be 3 times of IA naught. The fault current is 3 times of IA naught. So whenever fault is involved with the ground, we are having the fault current is 3 times of IA naught in LG and LLG, but not in LL and triple L, right, or triple LG faults. We will get those conditions clearly. And whereas the fault current IF is equivalent to, so EA1 divided by only the positive sequence impedance ZA1. So whenever you are having some fault impedance because of that fault location, so we can write that fault impedance as ZF in all the 3 cases, right? So sometimes it may be ZF and sometimes it may be 3 ZF also we have to write based on the situation. Clear? And whenever you are seeing the fault impedances, whenever you are having the fault impedances, so the fault impedance ZD double dash, here it is nothing but, or the subtransient impedance we can write as. It will be Z1 equivalent plus Z2 equivalent plus Z0 equivalent, right? So we can write the fault impedance also here, but I am not writing here. And whereas here it is ZD double dash is equivalent to Z1 equivalent plus Z2 equivalent. But whereas here it is ZD double dash is equivalent to Z1 equivalent plus Z2 equivalent, which is parallel to Z0 equivalent. Z0 equivalent. and whereas here it is ZD double dash is equivalent to only Z1 equivalent. If you see here, the fault impedance is very small or subtransient impedance is very small for triple L fault, so that we can say triple L fault is the most severe fault and LG fault is the least severe fault whenever the fault is occurring at the end of the transmission line. So if you see, whenever we are having a power system network like this, here is the load we are having. Whenever fault occurs at the end of the transmission line, right? So for a fault at the end of the transmission line, at the end of transmission line, these are the conditions. LG fault is least severe and triple L fault is most severe. LG fault is the least severe fault and triple L fault is the most severe fault. Triple L or triple LG fault is the most severe fault. Most severe fault. And coming to whenever the same fault is occurring at the terminals of the generator, right? So whenever the same fault is occurring at the terminals of the generator, so here we are having the fault. Now we can say the fault at the terminals of the generator. For a fault at the terminals of the generator. So in this case, we have to say the LG fault becomes the most severe fault. LG fault is the most severe fault and the remaining faults are less severe than that of this LG fault. Clear? And coming to the students, the next syllabus of the power system stability analysis, the last chapter. So in case of the power system stability analysis, so we have to study about the definition of the bounded input and bounded output stability and the types of stability analysis and steady state stability analysis and transient stability analysis you have to study, and the derivation of swing equation as we are studying as a model of dynamic model of rotor. We are studying this, and inertia constant and problems on inertia constant H, angular momentum M and inertia I and the apparent power S and equal area criterion applications and its applications also we are studying, right? So we can expect only from power system analysis at least 7 to 8 marks, and these are some important concepts, right? And we have discussed something about LG fault also. I think the class is very clear for you, right? And so try to prepare well, and these are the most important topics from the power system stability analysis and power system analysis also, right? Thank you.